Hello and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about pulleys and strings and tension and all of that. This is of course another video in my short series about forces and Newton's laws and some applications of forces and Newton's laws and examples of specific types of force. So today's video, what we're looking at is what kind of force gets applied via strings and what do pulleys do within a system. Now, one of the things that we usually make as an assumption in physics, we need not make it, but it makes the problem simpler to make this assumption. So for good purposes being introduced to this is the idea of an ideal pulley or an ideal string. This simplification basically means that the pulley is massless and frictionless, and that the rope is massless. So there's no forces from friction, and these things do not contribute any mass to the system. Essentially, you can solve problems in which these things are not true, but they do complicate the problem somewhat. So as an introduction, we'll assume that they're massless and frictionless unless stated otherwise. And the word ideal usually makes this assumption. So what is it that strings do? Well, let's say that I have a couple of objects. Maybe there's one here, and now there's another one over here. And they are connected to each other via a string. So here's a string or rope that connects the two to each other. And I grab onto this object and I give it a pull. That causes the object to start moving. We're assuming, of course, that I'm pulling hard enough that I've overcome any kind of friction. So the object begins moving. And from experience, we know that if this object starts to move with some speed v, that if we do it gently enough, this one will also start moving with the same speed v. In other words, the string links the two of them together so that they kind of move together. Now granted, I can allow the string to become slack. So one of the other things with this ideal string is that it is sort of slackless. So no slack enters into the string. That means that it's taut at all times. So this is another word of saying the string is taut. And what that basically means is that the string is applying some amount of force along its longitudinal direction, along its length. And so practically speaking, let's say that we blow up a bit of this string down here so that we're looking. So here's my string. It's held together by little segments of string, like so. And we can kind of take a what happens to each segment of string approach. And the answer is that there's some force on this segment of string from the nearest neighbor, and there's some force from the nearest neighbor in the opposite direction. So if this is segment 1, this is segment 2, and this is segment 3, then this would be F12, and this would be F32. These forces, really, they are along the string. So I tried to draw them along the string. They should be exactly opposite each other along the string. Alright, so that means that the net force on this piece of string is effectively 0, but it's also massless, so it doesn't matter too much. But now let's take another piece of the string. Let's highlight it in a different color. Let's take this piece of string that is attached to the block. Okay, so we want to blow up this piece of string, and here's the block edge. And so here might be some pieces of string. We'll call this string 1 and this string 2. Or maybe we look at this one on the very end. Well, this one on the very end is being pulled by the one next to it in this direction, F12. But there is no other string to the right of it to counter that pull. So in some sense, this piece on the end is applying F12 to the left. Now we've said that F12 down here and F32 are equal, and F12 up here should be equal to all of those. That force that we've labeled, that is tension. So F12 and F32, and if you really want to be pedantic about it, you could call this like 4 and 5, and so you could call this force up here F4, 5. All of those are equal to each other in magnitude, and they are all equal to the force of tension in the string. So we're labeling Ft as force of tension. Okay, this means essentially that this piece on the end, which we can say is like attached to the block, is experiencing a force of tension to the left. And if we go to the other end of the string, so here's the other end of the string, and again we blow it up, and again we draw the edge attached to the block, and here's my string once again. So maybe this is piece 6, piece 7, etc. This one, once again, is going to have some force pulling on it, F67 to the right. And so F67 is equal to all these other forces as well. That's the force of tension. Okay, that means that if we look at each of these two blocks, let's label this block A and this block B, then looking at the block, we can draw a free body diagram. So here, for example, is block A, the one that's on the left. And if I draw the forces that act on block A, there is some normal force from the surface that it's sitting on, and there is some gravity force. There might be friction, although we can treat it like a frictionless surface. We don't care in this particular problem. And then there is this force of tension towards the right. I'll draw a friction force just for the heck of it. Force of friction. And that would be force of friction on A, force of gravity on A, normal force on A. Force of tension just is Ft in this case. And if we look at the other block, the one that's on the left, the one that we've labeled B, we have recall that we said that there is a force being applied to the system. We could maybe call this force pull, or force P for pull. So we have a pull force, Fp. We have a normal force, F in B. We have gravity, Fg on B. And then we have, again, some friction, so friction on B. And we have the force of tension also on B. So if I wanted to figure out the sum of forces on each of these, on this object, object A, my sum of forces would look like the normal force A plus gravity for A, and in the system that I've drawn, these two will happen to cancel, so cancel, plus force of friction on A plus force of tension. These are all the forces that are on A. And so this, by Newton's second law, must be mass of A times acceleration. And on B, sum of forces on B should look like normal force on B plus gravity on B. And again, they cancel. So cancel. Plus the pull force plus the tension force plus friction on B. Okay, so now we say, okay, how do we add these forces? Well, they have to add as vectors, and so we set up the direction that says up is positive, down is negative, but we already canceled all the vertical forces. Left is positive, left is negative, right is positive. So on A, we would have Ft minus force of friction on A is mass of A times acceleration of A. Presumably it's accelerating to the right since we established that earlier in the problem. So this was the forces on A. And for B, we have the pull force to the right, we have tension to the left, and we have friction to the left. So this becomes mb times acceleration. And notice that the acceleration is the same in both. So let's note that tension is the same in both equations. Acceleration is the same in both equations. And you know, we don't really know the force of friction in these, and we don't know the pull force because they haven't been specified, but typically the pull force would be specified, as would be both masses, as would be the relevant coefficients of friction for both objects, or some equivalent. You know, maybe instead the weight is specified and the force of friction is specified for each, and the pull force is specified. That would be fine. Essentially, you have here two equations with two actually unknowns. Usually like the acceleration is unknown and the tension is unknown. So you could go about this and say like solve the system of two equations with two unknowns. And that's basically it. So we have set up our system of equations by basically drawing a free body diagram on each object and then literally adding the forces, paying attention to what direction they act in, and then invoking Newton's second law. I needed to invoke it down here as well, but mb times a, this pair of equal signs is Newton's second law. So that's that. What do pulleys do to our system? So what about pulleys? By and large, what the pulleys do is they sort of redirect force. So these redirect force. And they do that by essentially the string applies some force to the pulley and the pulley applies some countering force to the string, and that allows it to in some sense change directions. So if I have a system where I have again block, let's say B, so or block A up here, and then a string and then a pulley, and block A is block B is somewhere down here, and you know this is on some surface, I still have force of tension in this string in both cases. What the pulley is doing for me here is that it's allowing the force of tension to be sort of vertically directed for this hanging weight, and yet horizontally directed for the mass that's on the table. And notice that it's the same magnitude in both cases, we just happen to have a different direction that it's operating in, a different axis along which it operates. So again, if I wanted to draw my free body diagrams for A and B, for A, I would have a tension force, Ft, I would have a gravity, Fga, I would have a normal force, Fn, also for A, and I may or may not have some friction, F friction A. And so this is the free body diagram that goes with A. For B, what I would have is a tension force acting upwards, Ft, and then gravity acting downwards, Fgb, which would be mb times g. Again, if I set up the system of equations for this, I would have a system that looks like this, and if we put in signs and everything, we end up with these two equations. where I have kind of done something weird with the sign convention to say that up is negative and down is positive, but that's allowed with these pulley systems. So that's all for today.